me just tell you by way of Bruce, introducing Bruce. I've never been able to do this before. This is a 7-page resume. It's single space, it's small type, it's got very narrow margins. It's really one of the most impressive resumes I've ever seen in my life. Bruce is of course, an extraordinarily well-educated gentleman. He did his master's work in carbonate sedimentation, if I pronounce that correctly, at Duke. He studied at Cornell for his PhD work and got his PhD and I think what amounts to climate history from the University of South Carolina. Bruce Molnia is an explorer's explorer. It's looking at his face, it's hard to say this, but he spent 50 years in the field doing research, studying different aspects of geophysics, geology, particular dealing with how to do measurements there. He has authored or co-authored more than, I think, 350 papers, done numerous videos, and has really been committed. He's worked with Congress, done a great job there, and Bruce is a recent recipient, I think last year, recipient of the Lowell Thomas Award, and that's really one of our club's highest and most prestigious awards. And he's been a member of the Explorers Club for 40 years. So I'm very excited to hear what you have to say, Bruce. And so without going on any further, even though I probably should, I want to just turn the time over to you, and I'm going to mute my mic and mute my video while you speak. And people, be sure and get your questions on the chat line. Okay, thanks so much, Bruce.
Very good. Can you see my screen?
Yes, we can.
Okay. So the title, Hot and Getting Hotter, Why Should We Care, is a title that Joe suggested, and I agreed that I could tailor a presentation that I like to make that goes into some of the science of changing climate, what's happening to the Earth today, and also then leads to some of my research and my favorite aspect of glacier photography. So I'll begin and point out that most of the science that I'm going to present comes from 2 recently published climate assessments, one by the United States government, the 4th National Climate Assessment, and the other came out in September of last year, the Ocean and Cryosphere in a Changing Climate. Cryosphere is a part of the Earth system that deals with frozen water, so it's glaciers, snow, sea ice, lake ice, and permafrost. And I'll be talking predominantly about glaciers, but some of the other aspects of the cryosphere will probably come up.
Okay, Bruce, so, we don't have a screen share with you quite yet.
Oh, you don't? Let me exit. Let's try again. So
you just gotta love technology. However, we're good. And we've got all sorts of folks in the chat room that are saying hi, and a really nice audience. There we go, we can see it now. We've got your normal view.
There we go.
Perfect, that's it.
Okay, so these are the 2 reports I was referring to. The 4th National Climate Assessment and the Intergovernmental Panel on Climate Change, the IPCC's recent report on oceans and cryosphere in a changing climate. And so this talk is going to discuss global temperature change, global sea level change, and global glacier change with a focus on Alaskan glacier behavior. And so I've got 2 graphs up here. During the last 100 years, Earth's average temperature, this is the graph on the right, has increased more than 1 degree C, approximately 1.8 degrees Fahrenheit, with the Arctic and the Antarctic regions warming at least twice that amount. And with respect to Alaska, since 1949, Alaska has warmed more than 2.2 degrees C, which is average for the entire state of 4 degrees Fahrenheit. And it's raining, it's actually warming at a rate that is, 0.06 degrees Fahrenheit per year for the last 69 years. And during the 20th century, at locations around the globe that monitored sea level, the range of sea level rise was between 1.2 and 2.2 millimeters per year. That's 0.47 to 0.86 inches per year. That's based on tide gauges. We've had satellites monitoring ocean surface elevation since 1993, and they show a rate of between 2.4 and 3.8 millimeters per year. So we know that on average, since 1900, Earth's global sea level height has risen about 7 inches, about 20 centimeters. So let's talk about some basic terms. The terms global warming and climate change are often incorrectly used interchangeably. However, their meanings are significantly different. Global warming refers only to Earth's rising surface temperatures. The phrase is used to describe recent warming that is due in large part to the rapid increase of greenhouse gases in the atmosphere. And most scientists attribute this increase to human activities such as urbanization, population dynamics, agriculture, deforestation, and most significantly, the burning of fossil fuels. Now, Earth has had climate for as long as it's had an atmosphere and had water on its surface. So we're talking several billion years. And climate changes continuously due to a number of factors, not only temperature change, but also things such as geological processes, such as plate tectonics, volcanic eruptions, and even meteor impacts. The results of climate change include Earth's surface and ocean warming or cooling, glacier and sea level change, atmospheric circulation changes, changes in intensity and location of storms, changes in precipitation and humidity, and changes in the patterns of climate-related extreme events. So let's just look at what's happened in the US in terms of temperature. This graphic shows the temperatures of the US between 1986 and 2016 compared to 1901 to 1960. And you can see there are very few areas where it's blue or almost clear. Those are areas where there's been little or no temperature increase. In fact, some cooling in places. But anything that is pink to orange are areas where the temperatures increased anywhere between 1 and 3 degrees Fahrenheit. And as I mentioned before, in Alaska, since 1949, we've got an average of 4 degrees. So let's look at Alaska. These are where the first order weather stations are located. There are 21 of them in Alaska. And here is a table compiled by the Geophysical Institute at the University of Alaska showing temperature change from 1949 to 2018. And you can see that in many places where most of the temperature change is taking place is during the winter. And you can see here that at Barrow, which is the northernmost community in the United States, during that time period, winter temperatures increased an average of 9.8 degrees. And if you look at the lower right-hand side, you can see the total temperature change for all of Alaska, 4 degrees Fahrenheit, 2.2 degrees Celsius. If you just look at the last 42 years, you can see some really amazing changes. Barrow in autumn has increased more than 15 degrees. And Alaska as a whole, just during the last 42 years, is 2.8 degrees Fahrenheit, 1.55 degrees C. So we're seeing example in our own country of the extreme temperature impacts, changes, warmings that have taken place in the Arctic and the Antarctic. Here's an interesting graph also from the Geophysical Institute showing the mean annual air temperature departure from normal. So any year that's in blue is a year where the average temperature, or the temperature for that year, the average temperature was below a normal based on a period of a number of years. And anything you see in red is a period of time where that has been an increase. You can see that most of the increases have taken place in the last 25 years. Prior to 1978, 51 of 58 years had mean annual temperatures below the baseline, which is 1981 to 2010. And in fact, in 1956, the departure was more than 5 degrees Fahrenheit colder than the mean. Another graph, this shows average Earth temperatures from 1880 to the present, based on studies and data compiled by 5 different research institutions around the world. And again, you can see, you look on the left-hand side, that we're looking at changes from about minus 0.2 back in the 1880s compared to the mean, to as much as a degree above that in the last few years. Another indication of temperature change. This is from University of California, Berkeley. You can see here temperature change in the period 2014 to 18 compared with a decade at the end of the previous century. And clearly you can see some places have temperature changes in Fahrenheit more than 10 degrees, in Celsius as much as 6 degrees. And most of this warming, as you can see, is in the Arctic. There is insufficient data, but the data, if it did exist, would show similar trends in the Antarctic. So some of the impacts are very obvious. Glaciers are melting, and when glaciers melt, their meltwater ends up in the ocean. And if we look back in time, we can see that going back less than 20,000 years ago, sea level has changed dramatically. It was down more than 140 meters during the maximum glaciation of the Pleistocene about 20,000 years ago. And since then, sea level has risen by more than 435 feet. We'll talk about the implications of warming temperatures on future sea level change. We'll also talk about water on Earth, because it's a really interesting situation when you realize that there's a finite amount of liquid water on Earth, and it can be frozen or it can be liquid. Temperatures decrease, it freezes, glaciers expand, as was the case during the Pleistocene, when we had sea level down by more than 140 meters. Today, we're in an environment where glaciers are melting and sea level is going to rise. So, as we've mentioned before, sea level has been rising. We have the tide gauges, we have the satellite information, we have satellite data is not only looking at altimetry, we also have satellite data based on a NASA and French experiment called GRACE, which looks at gravity changes. And this is gravity because of ice masses, summer melting, winter snow accumulation, but it looks at long-term change over larger areas. And the GRACE data, which goes back almost 15 years, clearly shows dramatic changes, and we'll talk about those for the Arctic and the Antarctic a little bit later. So what's a glacier? Simple definition is a large perennial accumulation of ice, snow, rock, sediment, and sometimes liquid water originating on land, moving downslope under the influence of its own weight and gravity. In essence, it's a dynamic river of ice. And glaciers are characterized by their size, their location, and their thermal regime. So when I say thermal regime, we normally recognize 2 types of glaciers. Polar glaciers, which could have temperatures of minus 50 or more below 0, both Celsius and Fahrenheit, or temperate glaciers, where the temperature of the ice can be within a fraction of a degree of the melting point. In our current warming climate, it's these temperate glaciers that are extremely important, because a small amount of temperature increase that persists for years or decades can have a dramatic impact on these temperate glaciers. And what we'll see is that temperate glaciers throughout the world are melting, and in many places have disappeared. So we're going to focus on water for a couple of minutes. Water is the most abundant chemical compound on Earth's surface. And if you use an analogy that there are 1,000 drops of water to represent all the water on planet Earth, you'd learn quickly that there were 972 drops in the oceans and the inland seas. So 97.2% of all the water on Earth is in the oceans. There are also 21 drops in glaciers. So 2.1% of all the water on Earth is currently frozen as glacier ice. If you look at the remaining drops, they're less than 7, and 6 of them are in groundwater and soil. Less than 1 is in the atmosphere. Less than 1 would be in all the lakes and rivers on Earth, and less than 1 in all the living material on Earth, plants and animals. So think about that. 2.8% of all the water on planet Earth is freshwater, and 3/4 of this fresh water is frozen in glacier ice. So glaciers are the second largest reservoir of water on Earth, and the largest reservoir of fresh water. And where is this glacier ice? Well, 914 of 1,000 ice crystals would be in Antarctica, 79 in Greenland, and all the rest, less than 4 in North America with 1 in Alaska, less than 2 in Asia, and less than 1 everywhere else on the planet where we have glaciers. And so it's this 4 in North America, the 2 in Asia, and the less than 1 in every place else that are most susceptible to melting. And up until about a decade ago, this is where we're seeing the largest contribution coming from that was being contributed to global sea level change. But in the last 10 to 15 years, we've also seen significant increases in the amount of meltwater coming from Antarctica and Greenland. So if you were to melt all of the glacier ice in Antarctica, you could get as much as 65 meters of sea level rise. None of our climate models suggest this is going to happen. And in fact, the last time that Antarctica was ice-free was approximately 20 million years ago. If you melt all the glacier ice in Greenland, you can get as much as 6 meters, about 20 feet of sea level change. The last time this happened was only about 120,000 years ago. And it was that point in time that sea level was the highest it's been for North America's coastline for thousands and thousands and thousands of years. And it was that time that the fall line was cut into the coastal plain. The fall line is where streams coming off of higher ground, off of the Piedmont, actually have a significant number of waterfalls at an elevation of 6 or 7 meters. And this is a result of increased sea level 120,000 to about 110,000 years ago. So we've already discussed where the glaciers are that are temperate, and complete melting of the temperate glaciers would only produce about a foot of sea level change. So most of the sea level rise that we're concerned about is not from the melting of temperate glaciers, but the potential melting of Greenland and Antarctica. This diagram that comes from the IPCC, the Intergovernmental Panel on Climate Change, shows the relationship between glaciers, sea ice, snow, sea level change. So as glaciers melt and they lose their mass, that meltwater ends up in the oceans and sea level rises. As sea ice declines because of warming of the Arctic Ocean, that doesn't contribute to a rise in sea level, but it contributes to a warming of the ocean that has impacts on driving circulation and climate change. Other consequences that we won't really focus on, changes in ocean acidity, changes in the oxygen content, and warming oceans have significant impacts on the animals that live in them. The change in pH has an impact on carbonate shelled organisms such as clams and mussels. And so there's this intricately interrelated relationship between glaciers, oceans, temperature, sea level, and any number of other factors. One additional component of this is that when sea level rises, it's rising because of 2 factors. One is an increased number of molecules of water, that the water coming off the glacier melt into the ocean. The other is the molecules in the ocean actually create an increase in volume as their temperature increases. The distance between individual molecules expands. And so half of sea level rise that we're experiencing is due to new water. The other half is due to the increased temperature. This is a graph that shows what sea level has done the last 140,000 years. And that dramatic increase I mentioned beginning about 18,000 years ago is shown on the right-hand side of the graph. During that period of time, we were looking at sea level rising about 85 centimeters per 100 years, which is far more than we're anticipating seeing in any of the climate scenarios that focus on the impact of changing climate. So what's happening in Greenland? In Greenland, we can actually see during the 21st century an ice loss that has increased 725% from the pre-2000 time period. And between 2012 and 2016, Greenland lost 247 gigatons of ice. 1 gigaton is the equivalent of 1 cubic kilometer of water. So currently, Greenland is losing approximately 62 gigatons per year during the time period of record, 2012 to 2016. In Antarctica, it's even more extreme. Between 2002 and 2016, Antarctica lost 1,878 gigatons of ice, an average of approximately 125 gigatons per year. This is based on the NASA satellite data that is looking at the gravity, the GRACE satellite and the GRACE mission. So if you look at where this change is taking place, you can see that most of it is in coastal areas of Antarctica. It's actually getting colder as you move towards the interior of Antarctica. And the area to the upper left on this diagram, this graph, is where we were in 2002. And if you look at the very lower left, the lower left, the lower right, you can see where we were in 2016. You can see the 1,934 gigatons of melt in August 2015, cumulative gigatons measured by the GRACE satellite. But we're looking at dramatic loss of ice from Antarctica. So this is a photograph I took in January when I was down in the Antarctic Peninsula area. And this is a hanging glacier. But what struck me about this that was not normal were all of these channels, and I'm using my cursor, which I hope you can see. These are due to subglacial streams flowing under the ice. And these large semicircular conduits that you see here at the water edge are where meltwater streams enter into the Antarctic waters here. And so I saw this almost every place I traveled throughout the peninsula of Antarctica, something I was not expecting to see, and clear-cut evidence that melting is accelerating and having an impact on the glaciers throughout the Antarctic Peninsula and the coastal areas of Antarctica. So what's happening in Alaska? This is a graphic, the next couple of slides, that clearly gives you a time-lapse look at what's happening. This is a photograph from 1899 of Glacier Bay. This was actually taken by the American Harriman expedition. And let's watch what happens over the next 100+ years. And this is the same location. I'll go back just to put it in perspective. 1899 photograph I took in 2004. So we're going to spend the rest of the lecture looking at this type of imagery and look at a description of what's happening. So I use a technique called repeat photography. And as you can see in this picture, I'm sitting in a Zodiac with a 1900 photograph of the glacier behind me, the Wellesley Glacier. This picture was taken in 2000. And so you can compare images and do both qualitative and quantitative assessment of the differences. If you have the exact same perspective from the exact same location where the historical photograph was taken, I call that precision repeat photography. And there you can get some idea of the total extent of change. And what you see in most of these pairs, or in some cases triplets or even quadruplets, is that you go from an ice and snow covered area with bare bedrock to a much reduced glacier coverage, significant new vegetation, and lots of melt water. So we go from black and white to blue and green. So here's an example. These are 3 photos I took at the same location. The first in 1978. This is in Glacier Bay. The next one above it, 2003. I'm sorry, there'll be a third coming up a little bit later, but these two, same location. What's interesting, if you look at 1978, you can see algae growing on the bedrock. And the reason it was growing is that the glacier in the background, your glacier calved so frequently and created such large splash waves that the rocks were wet and the algae could find an environment where it could succeed. 2003, no glacier, no algae, and almost no vegetation. We'll look at this same location a little bit later. So I've done this at more than 225 locations throughout Alaska. Been able to successfully produce about 250 of these pairs and triplets. And in some of these periods of time that are covered by the span between photographs, much as 125 years. The areas I'm going to talk about are Glacier Bay, the Wrangell St. Elias National Park area, the Copper River Basin, Prince William Sound, and the Kenai Fjords. I'll show you examples of this similar type of repeat photography documenting change in most of these areas. We're going to start with Wrangell St. Elias. We're going to look at Barnard Glacier. So the 1936 photograph is an airborne picture that many of you have probably seen. It's by Bradford Washburn. And you're seeing the Barnard Glacier. I tried several times to duplicate this. This is a picture I took in 2006. And to me, when I look at the two, I can see significant thinning in the ice, especially along the margins. And I see numerous circular depressions on the surface of the moraines. These are locations where melting has been taking place, actively taking place. And so here's the pair of images side by side. We'll move over now to Kenai Fjords and take a look at aerials that I've taken of Bear Glacier. beginning in 2002, 2005, 2007, 2010. During that time period of 8 years, the terminus of the glaciers retreated more than a mile and produced a huge number of icebergs. And as you can see in the bottom right-hand photograph, there's no glacier ice anywhere near the shoreline or near the coast. That's important because we're going to look at another perspective of Bear Glacier in this next pair of photographs. This is 1923. This is a photograph taken at the time when the ice was still healthy, close to the shoreline. And then in 2006, what you see are not in situ pieces of glacier ice, but these are icebergs that we saw in the 4 aerials. And it shows the difference in this time period, 1923 to 2006. Notice the vegetation hasn't changed so much in the foreground, but once you get on the shoreline, very dramatic changes in what you see, and especially on the mountain coverage. Moving to another glacier, the largest glacier in the Kenai Fjords, McCarty Glacier, 1909 to 2006. Here it was in 1909. Fairly healthy looking terminus. There's vegetation off to the right in the mountains. By the 2000s, it had retreated more than 20 kilometers. And you can just see a small part of one of its tributaries on the very left-hand edge. Let's move over to Prince William Sound and look at Shoup Glacier. 1910 photograph. Shoup was a tidewater glacier sitting in the ocean. In 2012, it's retreated more than a mile, and you can see all of the vegetation that's developed in the interim time period. Neliwan Glacier. We're looking at an even shorter period of time, 1957. You can see the ice still looking fairly healthy. There's a tidewater lagoon in front of it, and the foreground beach completely devoid of any vegetation. Now we're going to jump ahead to 2011, and it looks like a totally different world. You can see the lagoon is filled in with sediment. It's now got marsh grass. There are mature trees growing, and all the glacier ice has disappeared from the field of view. So 1957 on the left, 2011 on the right. Move over to Glacier Bay. And we're going to spend the rest of this presentation talking about Glacier Bay. This Glacier Bay has one of the most robust photographic histories going back to the early 1880s. Glacier Bay was quote unquote discovered by John Muir in 1879. Within 4 years, tourism found Glacier Bay, and it coincided with the development of the Brownie camera. So within a decade, almost every tourist had their own camera and was taking pictures of Glacier Bay and a number of other locations. And there were steamers coming up from Tacoma and Bellingham, Washington, bringing tourists up who spent lots of time walking around the southern end of the Muir Glacier. So we'll take a look. This is a map on the left from the Park Service, and we're going to take a look at a number of photographs and actually first follow the retreat of the Muir Glacier from the position at the time of Muir all the way up to the present. And then we'll look at the west side of Glacier Bay and look at several of the glaciers and see how they've changed there. So this is a photograph from a book by a tourist, Edna Collis, 1890. Same location in 2004. And if you notice, the only glacier ice you can see here is this glacier about 50 kilometers away. And this is not even the Muir Glacier. This is a tributary of the Muir Glacier. The Muir Glacier is retreated off of the field of view. Another interesting look. This is a picture from 1892 by Harry Reid, one of the more famous geologists who spent time in Glacier Bay with John Muir and set up the first scientific measurements in several of the inlets here. This is a photograph he took in 1892. This is the same location in 2004. Again, notice the difference from ice and bare bedrock to blue water and green vegetation. Continuing further north, here's a steamer, one of the tourist ships that came from the Washington State ports, 1895. This is the Queen at Muir Glacier, in the same location in 2004. You go back and notice on the left-hand side, you get this little rounded knob of bedrock. Look at it in the next picture, the location is the same. So you do a lot of sleuthing, trying to find out where these historical photos come from. And often it becomes a matter of judgment. Are we in the right place? And so here I think we can clearly see the right place. Another example, notice the bedrock here in the center, just to the left of center, and a little bit of bedrock over here on the left-hand side. Notice how the tourists are dressed, especially this woman with a bustle, standing up on an iceberg, photographer with a morning coat and a top hat. This is how tourists visited Alaska in the 1880s. Same location in 2005. Again, notice the similarity in the features. Moving further, 1895, 2005. Notice the vegetation. Notice the beach. You can barely see the beach in this area because of the icebergs and the high water level, but there's actually no vegetation and they're just pebbles and cobbles. Here you've got shells, carbonate material produced by clams and similar types of crustaceans and mollusks, and dense vegetation. 1895, 2005. Another example where just a little bit of bedrock helps you pinpoint the location, 1895, 2005. Again, dramatic changes. During the period from John Muir's first visit in 1879 to the present, Muir Glacier has retreated far more than 60 kilometers. Now we're moving up to this area about 2/3 of the way up the inlet. The ice was here in 1948. It sat along the shoreline of Muir Inlet in 1966. This first photo you're going to see is 10 years later, 1976. The ice is still very close to the shoreline of Muir Inlet here. And you can see that McBride Glacier looks to be a fairly healthy glacier, 1976. Here we are, 2003. Notice the glacier's retreated. There's a bar here, which is the actual end moraine where the glacier was. See the icebergs grounded on it. Now we're going to go to 2019. There's no ice to be seen, although you can see icebergs. The glacier is several kilometers back and around the corner. So these are all three photographs that I've taken spanning a period of more than 40 years here in Glacier Bay. Continuing, one of my favorite pairs, 1941, picture by William Field. Thickness of ice here we know from geophysics is more than 2,300 feet. By 2004, the glacier's retreated another 6 miles off to the left. The only ice you can see is the tributary, which was much thicker back in 1941. And now we've got the trim line, this color change that marks the height of the ice. We've got more than 900 feet of water here. There's also a photograph taken from the same location in 1950. So this triplet is shown on the left. You get some idea of the location. The ice was here in 1941, retreated around the corner, was here in the 1970s. And in this picture in 2004, it's already retreated out of the fjord and is grounded on land. And we'll look at how that changes in a few images further on. So I showed you this one before, talked to you about the algae, 1976, 2003. This is a picture I took last summer, 2019. Notice how much vegetation and how dense the vegetation is and how it's covering the slopes here that were covered by ice on the earlier photos. Continuing on, this is the terminus of Muir Glacier. I took it while I was kayaking in Glacier Bay in 1978. I didn't know at the time that over here, just to the left of center, there was a 4,000-foot mountain. But when I came back, I could clearly see that what I thought were clouds actually were the bedrock ridges on the summit. And you can see that Muir Glacier is retreated and back on land in this 2003 photograph. Here's the same location in 2019. And the triplet showing the changes in a period here of, what is that? That's 22, 32, 30, just less than 45 years. Another view, 1980, same location, 2003. One of the more dramatic pictures I took while I was kayaking, 1976, same location in 2003. Some aerials now. One of my colleagues, Austin Post, took this photo of the terminus of Muir Glacier in 1986. I duplicated it in 2009, and then again in 2015. and then in 2018. And you can see Muir is no longer this pair of tributaries. They've separated, continues to retreat, continues to melt, continues to disappear. Let's look at a couple of other locations in Glacier Bay. But before we do that, here are 9 satellite images showing the loss of glacier ice in Muir Inlet from 1972 to 2018. So not only do we have ground-based pictures, but there are all sorts of other sources of information that help us confirm the rates of change and the magnitude of glacier ice loss throughout Alaska and other places as well. So we're going to move over to the other side of Glacier Bay, the Reed Inlet. And this is a photograph taken in 1899 by Gros Curl Gilbert, one of the more famous geologists of the time. And when he took this picture in 1899, John Muir was standing next to him. Muir was part of the scientific team on the Harriman expedition. So this is what it looked like in 1899. 2003. So 104 years later, you can barely see the ice on the very left-hand side here, but notice the vegetation. I had the opportunity to go back there last summer, and this is what the view now looks like. So look at the dramatic changes, 1899, 2003, and 2019. Moving along, this is a photo by Al Brooks, 1924, same glacier, Reed Glacier. 1941, small amount of change. 2003, almost no change in that 60+ year time period. And then 2019. One of the things I need to explain, this is a moraine in the foreground, and there's about 15 to 18 feet of tide here. So in some of the pictures, I was able to be standing on the moraine, and other times it was submerged and we're in a boat over the moraine. But this is all the same location during the time period spanning 1899 to 2019. An aerial that I took of Reed Glacier in 2004. You can see the moraine partially exposed here in the foreground. In the same location in 2018. Much more retreat on the side, and the glacier has retreated far back from the shoreline. Another glacier called Lamplugh Glacier, just adjacent to Reed. 2004 photograph. It actually advanced between 2004 and the next decade, and now has retreated back several hundred meters. So some of these glaciers undergo short-lived changes in position. A number of climate deniers will take that as evidence that global warming is not real, but this is part of the natural behavior of glaciers. They have winter advances. You get a heavy snow year, and it may translate to a brief advance of the terminus. But glaciers do vary, but generally we're seeing significant amounts of retreat and disappearance, and lots of glacier ice thinning. Johns Hopkins Glacier is a glacier that advanced after the 1920s and has pretty much held its position. So this is a picture from 1931 when it was quite a distance back from where it is today. So 1921, 1978, my first photograph of it, and then a picture that was taken last year, 2019. So between 1978 and 2019, the terminus position has just fluctuated a little bit, but it advanced significantly between the 1920s and where it is currently. Another glacier, this is Carroll Glacier. At the time this picture was taken in 1906, there were 600 feet of water behind Triangle Island, which is in the foreground. When I revisited it in 2003, the entire area was filled with sediment. And what you see here is just a thin surface of water over a stream channel in the middle of the image here. See the vegetation, dramatic change. See the glacier is not even visible. You just have this large amount of sediment and moraine here. Another view of Carroll from up on the mountainside. Again, 1906. You can see the deep water here in the foreground. And here we are in 2004. The entire thing is filled with sediment. You can see the moraine ridge here. So I'm going to stop there. I hope you have seen several things. Number one, that Earth is dynamic and changes rapidly, that the water that's not frozen in glaciers ends up in the oceans, and it can change elevation of the seas dramatically. Why is that important and why should we care? Because more than 1 billion people live at elevations where just a couple of meters of sea level rise could completely inundate where they are. And numbers of those areas are within the United States. along the coast of Florida, all of the states along the Gulf of Mexico, and significant numbers of locations within Texas. So I'll stop there and take your questions.
Bruce, Joe here. Hey, thank you so much. That's an amazing presentation. That's the kind of data, hard data that we need. And of course, those photographs are irrefutable evidence that there is global warming. It's irrefutable, and it's a little bit frightening as well. In my conversations with people, it becomes clear to me that most people understand that there is climate change. They understand that we've been through 5 major ice changes and ice ages and scores of climate change periods that are in the record. And yet I'm, Bruce, really surprised to find that educated, intelligent people do not seem to be alarmed about this aspect of global warming, of climate change and global warming. And they kind of go about their merry business. I'm surprised. I have 2 grandkids that I love, and I'm worried about their future and their grandkids. So it's a real big issue that I think we ought to be paying attention to. I think it's important for us to ask 2 or 3 questions, which I want to ask you. One of them is, but for the impacts of human beings on the planet, the industrial revolutions that have gone on in the past, that are going on now, and there's some yet to occur in various parts of the world. If you set aside the impact of humans on the climate, would the Earth be warming or cooling today, or would it be at a level state? That's a question that some people have asked me. Can you answer that?
So, give you a little bit of historical perspective. There was a period of time from about 1200 AD to anywhere between 1750 and 1900 when glaciers expanded on all of the continents. It's called the Little Ice Age. Some places like southeastern Alaska, glacier retreat began around 1750. And that's what was captured in some of the retreats that were photographed in the 1880s. What we're seeing is the rate of retreat accelerating. As I showed you on those charts earlier, showing the difference between the time period before 1949 in Alaska and the increase since the 1980s. So yeah, if humans weren't doing anything, we'd probably still see glaciers melting, but at a much slower rate than we are actually observing. And just to expand on something you mentioned, that diagram I put up showing 140,000 years of sea level variability. Every time it dropped, it was because glaciers were expanding on land, and every time it rose, it was because it was warming to the point where glaciers were melting. So throughout geologic time, glaciers have come and gone. What we're seeing today is an increase in the amount of solar radiation that gets reflected back to the Earth's surface and is causing the warming not only of the atmosphere, but of the Earth's surface. And this is due to activities that are predominantly related to human activity. If humans had never evolved, we'd still see this natural variation that we have taking place for literally billions of years. But what we're seeing is a significant acceleration in the rates of change.
And that actually leads to my next question, which is, can we actually quantify how much impact there is on the climate that's causing this accelerating global warming from human beings as compared to what was going to occur naturally? Can scientists say, okay, there's this much that was going to happen naturally, but now we've got that much? Can we identify that?
That is an interesting question because it involves an aspect of science called modeling. People take all of the different types of climate data and they put them in a variety of models that look at, well, if you have so much increase in solar radiation, what's going to happen? They have data they can compare it with, such as the satellite altimetry data that I talked about. The ocean height changes clearly show an increase in the amount of meltwater entering the oceans. But if you're looking for a simple, single, straightforward place where you can measure and say, well, the temperature without human activity would have been half a degree cooler. No, it's all based on observations and trying to factor in a number of different things. What's taking place because of normal solar radiation, what's taking place because of what's reflected and not escaping. So one of the basic principles that you need to keep in mind in terms of why this is happening is that carbon dioxide, methane, water vapor are called greenhouse gases. And what they do is they accumulate in the atmosphere at an accelerated rate compared to what we had observed 50, 75 years ago. And what they do is they trap solar radiation that normally would have been reflected off of the Earth's surface and lost back to space. And they cause it to be re-reflected to the Earth's surface. And that can be measured. You can measure the watts of energy reaching the Earth's surface over time and compare it with other periods of time. And when you look at the amount of greenhouse gas, there are models that calculate what the impact of these greenhouse gas molecules are in terms of causing this increased reflection of energy back to the Earth's surface. But a simple, straightforward measurement, no.
Okay. So again, I'm looking for very specific answers to something that's probably pretty nebulous. So a real fundamental question is, at what level of temperature rise is it worldwide? 5 degrees Fahrenheit, 8 degrees Fahrenheit? At what point do we begin to actually see mass population relocation, loss of arable land leading to starvation, war, pestilence, loss of infrastructure? Is there some number that you can point out that's the point at which things really get to be a problem for my grandchildren or their grandchildren?
So if you ask the authors of those two reports I pointed out at the beginning, they would tell you, we really need to keep it under 1.5 degrees C change, global change. You get beyond 2 and it warms much more rapidly and sea level rises more rapidly. It gets well beyond 2 and then it becomes an unknown ballgame. So each of those reports presents different scenarios at rates of warming, rates of sea level rise. If you think about where people live, some people already are being impacted by these changes and need to migrate. There are any number of communities at risk. There are any number of places where inundation from storm surge that didn't impact areas a decade ago or 2 decades ago, and certainly 100 years ago, is far greater than today. So it depends on where you are. There's some places that will get more habitable as temperatures continue to increase. There are many places where the consequences of glacier melting may be far more significant. The other thing to think about is that lots of places on Earth get their fresh water from glacial runoff. The temperate glaciers disappear, there's no more glacial runoff. And so agriculture, potable water, water for industry disappears. So where do you see this happening first? You can look at any number of places where it already has impact, like the Sahel in North Africa, the India-Pakistan border area where the Indians and the Pakistanis virtually at war over ownership of the discharge from a particular glacier, the Sichuan Glacier. You can look at places in the Pacific where coral atolls that have long-term habitation are now being flooded almost on an annual basis. People are being forced to relocate. So you can pick your area and pick your consequence.
So I just have 2 more questions, and I'm going to reverse them in the order I intended to ask them, because I think this relates to what you're talking about. So here we are, Bruce, in a world of rising popularity, of nationalism, of autocrats and authoritarian, and so I worry that in that environment that we are all in on a worldwide basis, are we going to grapple with a problem? So that brings me to a question. The question is, I know that you scientists talk about various tipping points, and I think you talk about a global tipping point. Is there a global tipping point at which it cascades over the cliff and it's either impractical or virtually impossible to get? Humans can no longer stop the problem. Is there a point at which all bets are off and we lose major population in the world?
That's a hard question to answer because there's so many variables and every place is different. But if we have continued warming, we have continued acceleration of melting in Greenland and Antarctica, you can make a statement that probably within 100 years, no one will be able to inhabit areas that are today located between sea level and a meter above sea level, unless you put in huge infrastructure to protect the coastline from inundation. Now, there are only a few countries that have the resources to do that. And in many places, the question becomes, is the cost of protection worth the cost of what you're protecting? There are going to be many other areas where temperature is going to warm or atmospheric circulation is going to change, and it may make agriculture as we know it no longer possible. There are other places that will become, as I said, better suited for growing certain things. You're seeing migrations of all sorts of organisms to places where they were not native, sometimes having really dire consequences, such as all of the spruce bark beetle and pine bark beetle infestations that are killing trees in the Rocky Mountains all the way through Alaska. You're seeing parasites of one kind or another migrating to areas where they never could have survived because of winter temperatures being too cold. So there already are many consequences. When you talk about a tipping point, it depends on what you're looking at. There are probably so many different tipping points based on whatever parameter you're actually trying to cope with.
I want to take that as an answer that there may not be a quite great global tipping point that's very likely where everything is gone. Am I being too optimistic?
Well, if you ask me what's the fundamental problem, I would tell you, look at the population of Earth today compared to even 100 years ago. We have so many people, we are taxing Earth resources like they've never been stressed before. You add warming temperatures and rising sea level, and it becomes a totally different problem. And so we may have well passed whatever tipping point it is that we'll discover 100 years from now really resulted in significant differences.
Okay, and here's my final question that I'm going to turn over to Nancy, and she can take give you the question from the people that are listening in. A couple of friends of mine, Sam Oliver and Don Berkusiak, have said, look, this is not just a U.S. problem. It's not just our problem in this country. It's a worldwide problem. It's a problem for industrialized nations, for third world nations. The impoverished and the empowered have very different agendas in the world. Here's their question. The question is, how do you get the world society to come together and recognize this is a real problem and say, okay, now it's time. We know that that carbon that goes in the air stays there for maybe tens of thousands of years. You can't get it back very easily. How do we get people to stop and say, okay, we're going to make the Paris Climate Accord really work, and we're going to go farther than that, because that probably doesn't afford it. What do you do to be able to get the world to come together?
That's a very good question. And it's certainly a question that I don't think anybody has come up with an answer. Every country treats the climate accord differently. We ignore it. There are many countries that are doing the best they can with whatever resources they have to try to stabilize and adapt. We've gotten from the point of changing to mitigating and adapting. And so on a global scale, every place, based on what it is experiencing, is going to come up with its own unique answer. But it's a global issue. If you continue, if you assume that the primary cause of this is increased greenhouse gas buildup in the atmosphere. And the largest countries that are contributing greenhouse gases don't do anything. It's very hard for the rest of the world to solve this problem. And until we reach a point where we make a decision, and it's going to be a hard decision that we have to change our lifestyles in order to try to reduce the rate of change or find some way of reaching a stable environment, if that is even possible, we're not going to make progress. So there are many other people who can give you better answers or more detailed answers. But I think, you know, as a citizen of planet Earth, each of us should be concerned about not only what we're doing now, but what the consequences will be 50 or 100 years from now. You mentioned your grandchildren. That's a really interesting question. What's going to happen? Where will sea level be in South Texas 50 years from now?
I hate to tell you this, Bruce, but when I was coming back from the boat this afternoon, I talked to a friend of mine and asked him these questions. And he said, well, my concern about global warming is how much is my property on the coast going to go underwater in the next 20 years? After that, I'm dead. And I thought to myself, it's just an amazingly short-sighted. That's the most short-sighted thing I've ever heard an adult say. Okay.
Yeah, I agree. It's short-sighted, but unfortunately, there are many governments that make that same statement.
Yeah. All right. Well, I'm going to come back and properly thank you in a minute. I want to turn this over to Nancy. Okay, Nancy, do we have questions? It's up to you, girl.
All right. Thank you, Joe. And thank you, Bruce. That was amazing and very informative. Those images are stunning and powerful. We do have some questions that have come in from our chat. So Brian Hansen, our Explorers Club buds, what? I am really having a hard time with words tonight. Our Explorers Club ombudsman, Brian Hansen, has asked a question. Bruce, can you see Greenland turning green in our lifetimes?
I doubt it. But, you know, interestingly, there was a period of time when Vikings lived in Greenland back almost 1,000 years ago and sustained an agricultural community for a period of about 250 to 300 years. And then the Little Ice Age destroyed that. So Greenland will become greener. There is vegetation in parts of Greenland today, but not in the short term. Although we're seeing such an increase in the rate of melting that there'll be much more exposed bedrock around the southern perimeter of Greenland than any of us would have anticipated 20, 30 years ago.
All right, thank you. Our friend Jonathan Reynolds says, fascinating data, Bruce. Thanks for the informative presentation. I remember seeing the penguin colonies in Antarctica being affected by ice melt back in 2014. Do you happen to know the current effects on wildlife, like penguins, seals, and even whales in Antarctica, and how migration patterns are being affected? Also, what about long-term concerns?
That's a topic that we could spend the next hour talking about. I was in Antarctica in December and January this year, and I talked to a number of biologists who I was traveling with, and every species has a different impact. It was being impacted differently. Some species of penguins are actually increasing. It's more a function of their food source. Krill is the primary source of most penguin diets. Some species, the larger ones, eat fish as well. So totally unrelated to climate is illegal fishing. And that's having a major impact on fish stocks in and around Antarctica. So climate change may not be the single stressor on many of these species. There's still a couple of countries that conduct whaling in and around Antarctica. Even though the world has banned it, there are countries that have quote unquote permits for scientific investigation of whales. And so that is taking a toll, although the whales in general are increasing in numbers. But that's a complicated topic, and it's not one I'm really qualified to answer, but I do know it's quite a variable response.
I'm so glad you brought that up. I just a few years ago did a documentary about the challenges in Antarctica with krill being taken for the high demand for krill oil, And of course, you know, who doesn't love a delicious Chilean sea bass
Right.
at their gourmet restaurant? Unfortunately, sea bass is Patagonian and Antarctic toothfish that are being overfished. So yeah, there's a lot of factors that muddy the waters there. So let me jump to the next question though. We've got, let's see, I've got a long chat list here from Gary. He wanted to know, does increased vegetation suggest possible lowering of rates of temperature increase?
In theory, it should. But we don't have, you know, what we're looking at now in many places is less than 100 years of vegetation development. So you haven't gotten to large trees in many places. You're still looking at woody shrubs and you know, grasses and so on. Once you start developing a larger tree cover, it may be a positive factor in terms of temperature reduction. But in the really critical areas where we're seeing rapid melting today, it's still early, still too early to see vegetation coming in. Parts of Glacier Bay Glacier Bay reached its maximum ice extent somewhere around 1750 and has had continuing retreat since then. So the lower parts of Glacier Bay are extremely dense rainforest with really, really lush vegetation. And I'm sure they do quite a bit to mitigate temperature in those areas. But the upper part, as you saw in many of the pictures, is still bare bedrock.
And then our beloved Brian Hansen asked another question. Where are the first islands you see going underwater?
Well, places like the Marianas, the Marshall Islands especially, there are any number of low elevation coral atolls, which by nature subside anyway, and then coupled with rising sea level, because their maximum elevations are only a meter or less, those are the places where you can already see the consequences.
Okay. Brad Scott says, if I understood correctly, temperature change is greater at or near the poles. In some parts of Alaska, there are vast differentials in temperature change. Why?
Elevation, for one, cloud cover, latitude. So there are any number of factors that impact. Remember, Alaska from north to south is almost the same distance from the Texas coast to the Canadian border.
Mm-hmm. Yes, when I was in Alaska last, they love to brag about being greater than twice the size of Texas whenever they encounter Texans. Yeah.
Yes.
All right. Let's see. Bob Kaufman asked, do scientists working for the USGS have concerns about retribution based on statements they make on climate change?
Some do. I have friends who have left working for government because they felt they were being constrained. In an official capacity, it would be difficult to make a formal presentation. You know, I have to state what my situation is. I retired from the USGS and work with them as a volunteer. So when I speak, I'm speaking for myself, not for the US government, not for the US Geological Survey.
Thank you. And let's see, Ray asked, the glaciers in the Alps and Himalayas supply runoff to millions of people. Is glacier retreat there as severe as in Alaska?
It is. In fact, I was just sent an article yesterday about one of the glaciers on Mont Blanc, which has been breaking up and actually shedding large pieces of ice. It's a steep hanging glacier. It's caused a closure of the roadways in the area and all the hiking trails. And it's part of sort of late stage collapse of lower elevation glaciers. So there is a similar study in the Alps that a colleague of mine has been doing for years, where he uses postcards from the 1890s onwards and has revisited several hundred places in 5 different countries in Europe that have glacier cover. And some of the retreats are as dramatic as you see in Alaska.
Awesome. Okay, Ray Hankemer, that's your answer there. And then from Rob Muir, he would like to know, Is global warming always a bad thing? Dark ages in Europe meant mostly poverty. After warming period, serfs could grow more and have more money. Sorry, I didn't read that with the right inflection there. And Europe entered into relative prosperity. The ozone hole is closing over Antarctica. Does that help?
So global warming, is just a statistical description of complex processes that are taking place everywhere on the Earth's surface. And when you say, is it good or bad? It depends on where you are personally and how much of a humanist you are and how much you care about your fellow Earth citizens who may be thousands of miles away in an environment where just a small amount of warming will inundate their property in less than 20 years.
All right. Well, that's it for all the questions. And Bruce, I can't thank you enough. What a fantastic program you've put together for us today. Joe, did you have some closing comments you wanted to make?
No, except that I just want to say this has been a wonderful, spectacular experience. We can't possibly, Bruce, thank you so much, too much for being here and, and for all the work that you've done throughout your life. It's people like you that move humanity forward and help us all advance and help us be aware of where we are and what our obligations are to our fellows.
Wish
Nancy?
you luck with that, Brandon. That's great.
Nancy, can I just make a quick announcement about our next event, next speaker?
You bet. Please do.
Okay, great. So, Bruce, we think so highly of your Washington Explorers Club group. I think that's the correct way you say it, that we're rating all your talent. We're going to talk to Sarah Yosman, and she's going to speak on September the 24th at 7 o'clock. That's a Thursday night, assuming that works for all of you folks. Sarah's a really interesting person. She's an archaeologist. She's done research in a lot of places in Europe. She's finished 2 master's degrees, about to finish her PhD, and she specializes in imperial Rome and archaeology there, and she specializes in science and doctors and cults, and specifically about pandemics in ancient times. And we had a wonderful conversation. I think everybody will enjoy learning about that. She's a really direct, clear speaker, and we're going to talk about what happened, how people have responded over history to pandemics as compared to how they are responding now. And I think we're going to see that human nature doesn't change very much. Medicine does, but human nature doesn't. So that's September the 24th, 7 o'clock Central Standard Time, Thursday. We hope you will all tune in, and Bruce will try and stay away from your crowd for a while.
Thank you very much.
All right, that's great, Joe. And having been the program chair recently and know how much work that is, thank you so much for putting these together. I appreciate it more than you'll ever know. You've got some great programs planned for us ahead. I wish we were together face to face. It's so glad to have the Washington group with us tonight, as well as our Texas group and friends of the Texas group, and Dr. Bruce Molnia. Thank you for the time that you've taken, not just for tonight's presentation, but I know you put a lot of effort into it, and we much appreciate all of your efforts on behalf of the Texas chapter.
My pleasure. Thank you very much for inviting me.
All right, and we will see everybody September the 24th, and stay safe, stay healthy, keep washing your hands, and don't touch your face, and all those good things, and we'll come out of this the other side stronger and better. Thanks a lot, and have a good evening to everybody.